Section 2.2 Shannon's information measures. There are four types of Shannon's information measures, namely entropy, conditional entropy, mutual information, and conditional mutual information. We will start with the definition of entropy. The entropy Hx of a random variable x is defined as minus summation x px log px. Here the convention is that the summation is taken over the support of x. The base of the logarithm may or may not be specified. When the base of the logarithm is specified to be alpha, we write Hx as h sub alpha of x. Entropy measures the uncertainty of a discrete random variable. We are going to explain this later in the course. The unit for entropy is the bit if alpha is equal to 2, is the net if alpha is equal to e, where e is the base of the natural logarithm, and is the dit if alpha is equal to d for some positive integer d. Note that the notion of a bit in information theory is very different from the notion of a bit in computer science. Here's a remark. The entropy of x depends only on the distribution of the random variable x, but not on the actual values taken by x. Hence, it is also written as the entropy of the probability distribution p sub x. Here's an example. Let x and y be random variables with both alphabets equal to 0 and 1, and we let px0 equals 0.3, px1 equals 0.7, and py0 equals 0.7, and py1 equals 0.3. Obviously, the random variables x and y have different probability distributions, but they have exactly the same entropy. There is a more compact way to represent entropy, namely in terms of expectation. Here's our convention for expectation. The expectation of g of x for some random variable x is equal to summation x px times gx, where the summation is over the support of x. We also have linearity for expectation for our convention, namely expectation of fx plus gx is equal to expectation of fx plus expectation of gx. With this convention, we can write entropy of x equals minus expectation of log px equals minus summation x px log px, where gx is equal to log p of x. In probability theory, when expectation of g of x for a random variable is considered, usually g of x depends only on the value of x but not on the probability of x. In information theory, this is not the case. We now introduce the binary entropy function. For gamma between 0 and 1, define the binary entropy function hb gamma equals minus gamma log gamma minus 1 minus gamma log 1 minus gamma. Note that when gamma is equal to 0, we have minus gamma log gamma equals minus log 0, which is undefined. Likewise, when gamma is equal to 1, we have 1 minus gamma log 1 minus gamma equals 0 log 0, which also is undefined. So we take the convention that 0 log 0 is equal to 0, and this is justified because by L'Hopital's rule, a log a tends to 0 as a tends to 0. For a binary random variable x with distribution gamma and 1 minus gamma, the entropy of x is equal to hb evaluated at gamma The binary entropy function hb of gamma achieves the maximum value 1 when gamma is equal to 1/2. When gamma is equal to 0, hb gamma is equal to 0. When gamma is equal to 0.5, hb gamma is equal to 1. When gamma is equal to 1, HB gamma is equal to 0. Here's the interpretation of the binary entropy function. Consider tossing a coin with the probability of getting a head equals gamma and the probability of getting a tail equals 1 minus gamma. Then HB of gamma measures the amount of uncertainty in outcome of the toss. When gamma is equal to 0 or 1, the coin is deterministic and HB of gamma is equal to 0. This is consistent with our intuition because for such cases, we need 0 bits to convey the outcome. When gamma is equal to 0.5, the coin is fair and HB gamma is equal to 1. This is consistent with our intuition because we need 1 bit to convey the outcome. When gamma is between 0 and 1, and gamma is not equal to 0.5, the binary entropy function HB of gamma is between 0 and 1. That is, the uncertainty about the outcome is somewhere between 0 and 1 bit. This interpretation will be justified in terms of the source coding theorem later in the course. Next, we define the joint entropy. The joint entropy HXY of a pair of random variables x and y is defined as minus summation xy pxy times log pxy. This can be written as minus expectation of log of pxy, where pxy refers to the probability of the random variables x and y. The next definition says that for random variables x and y, the conditional entropy of y given x is defined as entropy y given x equals minus summation xy pxy log py given x, which can be written as minus expectation log of py given x. Now note that when we cover up the conditioning on x, this reduces to the usual definition for the entropy of y. Namely, entropy of y is equal to minus expectation of log of py. Now entropy of y given x is equal to minus summation xy pxy log py given x. Now pxy is equal to px times py given x. Now by moving the px outside summation y, we can further write this as summation x px and then bracket minus summation y py given x log of py given x. Now note that the inner sum is the entropy of y conditioning on a fixed outcome small x. To see this, we cover up the conditioning on the small x. We realize that this is just the entropy of y. And by restoring the conditioning on the small x, we realize that this is just the entropy of y conditioning on a fixed x. So we denote the inner sum by entropy of y given x for a particular small x, and we have entropy of y given x equals summation x px times entropy of y given x for a particular x. In other words, the conditional entropy of y given x is equal to the weighted sum of the conditional entropy of y given a particular x over the distribution px. Similarly, we can write entropy of y given xz as summation z pz times entropy of y given x and a particular z, where entropy of y given x and a particular z is equal to minus summation xy pxy given z log of py given xz. Note that when we cover up the conditioning on a particular z, this formula reduces to the usual definition of entropy of y given x. In proposition 2.16, we are going to prove two very useful formulas. First, we have entropy of xy equals entropy of x plus entropy of y given x. By exchanging the rows of x and y, we also have the second formula, namely entropy of xy equals entropy of y plus entropy of x given y. Now we are going to prove the first formula. Consider entropy of xy equals minus expectation of log of pxy. Now pxy can be written as px times py given x. And then minus expectation of the log of px times py given x is equal to minus the expectation of log of px minus expectation of log of py given x. The first expectation is equal to entropy of x, while the second expectation is equal to entropy of y given x. This proves the first formula. The interpretation of this formula is the following. Recall that entropy measures the uncertainty of a random variable or collection of random variables. So hxy denotes the uncertainty contained in the random variables x and y. Now on the left-hand side, consider that x and y are revealed in one step, and so the uncertainty is equal to entropy of xy. Now on the right-hand side, imagine that we reveal x and y in two steps. In the first step, we first reveal x, and for this, the amount of uncertainty revealed is equal to entropy of x. And then in the second step, we reveal y, and the amount of uncertainty revealed in the second step is equal to entropy of y given x. Now this formula says that whether you're going to reveal x and y in one step or in two steps, the total amount of entropy is actually the same. Now we define the mutual information between two random variables. For random variables x and y, the mutual information between x and y is defined as ixy equals summation xy pxy times log of pxy divided by px times py. This can be written as expectation of log of pxy divided by px times py. Note that ixy is symmetrical in x and y. This is evident from the formula for ixy given above. Now we derive an alternative form for ixy. First, ixy is equal to summation xy pxy log pxy divided by px times py according to definition 2.17. Then pxy divided by py can be written as px given y, and so we have ixy equals expectation of log of px given y divided by py. However, it is not apparent from this form that ixy is actually symmetrical in x and y. The next proposition, 2.18, says that the mutual information between a random variable x and itself is equal to the entropy of x. That is, Ixx is equal to entropy of x. First, we recall the definition of the mutual information between x and y. With y equals x, we have Ixx equals expectation of log of pxx divided by px divided by px. Now pxx is equal to px, and so we have px cancelling with this px here, and this becomes minus expectation of log px, which is just the entropy of x. So we have proved that the mutual information between x and itself is equal to the entropy of x. For this reason, the entropy of x is sometimes called the self-information of x. Proposition 2.19 consists of a few useful formulas for mutual information. First, Ixy is equal to hx minus hx given y. This formula says that the mutual information between x and y is equal to the difference between the entropy of x and the entropy of x after knowing y. This is consistent with the interpretation that the mutual information between x and y is equal to the amount of information that we can obtain about x by knowing y. Second, Ixy is equal to hy minus hy given x. This formula is obtained from the previous one by exchanging the rows of x and y. And then Ixy is equal to hx plus hy minus hxy. Provided that all the entropies and conditional entropies are finite. Now this is to avoid the situations that we have infinity minus infinity, and the proof of proposition 2.19 is left as an exercise. Now for this formula Ixy equals hx plus hy minus hxy, we notice that it is analogous to a set-theoretic formula mu A intersect B equals mu A plus mu B minus mu A union B, where mu is a set additive function and A and B are sets. The formulas we have obtained so far for the information measures for two random variables x and y can be summarized in this information diagram. First, we have a set on the left-hand side that represents entropy of x. The set on the right-hand side represents entropy of y. And then the union of these two sets represents entropy of xy. This region represents entropy of x given y. This region represents entropy of y given x. And the intersection of the two sets represents the mutual information between entropy of x and y. Next, we define conditional mutual information. For random variables x, y, and z, the mutual information between x and y, conditioning on z, is defined as Ixy given z equals summing over all x, y, and z, pxyz log pxy given z divided by px given z, py given z. In terms of expectation, this can be written as expectation of the log of pxy given z divided by px given z, py given z. Note that by removing the conditioning on z, we obtain Ixy equals expectation of log of pxy divided by px divided by py, which is simply the usual formula for mutual information. From this formula, we note that Ixy given z is symmetrical in x and y. Similar to entropy, we can also write Ixy given z as summation z pz Ixy conditioning on a particular z, where Ixy conditioning on a particular z is equal to summation xy pxy given z log of pxy given z divided by px given z, py given z. Now note that by removing the conditioning on a particular z, this reduces to the usual formula for mutual information. Proposition 2.21 says that the mutual information between a random variable x and the self, conditioning on a random variable z, is equal to the conditional entropy of x given z. That is, the mutual information between x and x conditioning on z is equal to the conditional entropy of x given z. Now, by covering the conditioning on z, we see that it reduces to Ixx is equal to entropy of x, which is just proposition 2.18. Proposition 2.22 consists of three formulas for conditional mutual information. This proposition is just the conditional version of proposition 2.19, so we're going to skip the details. To end this section, we just mentioned that all Shannon's information measures are actually special cases of conditional mutual information. To see this, we let phi denote a random variable that takes a constant value. Then the entropy of x is equal to the mutual information between x and itself, conditioning on a constant variable. Conditional entropy of x given z is equal to the mutual information between x and x, conditioning on z. And the mutual information between x and y is equal to the mutual information between x and y conditioning on a constant variable.